Thank you. So should I go ahead and start sharing my screen?
Just give us a couple of minutes. I think we're
Okay.
still waiting for a couple of people to come in. I'll play a little bit more music,
Okay, sure.
and then we'll get started.
Okay, sure.
And you are going to love the music.
It's good.
Okay, that was Ritzvi's Ligi going out to Brandon from WNASA Goddard, coming to you at 10.7 centimeters. All right. So this is our last day of the summer school. I think Brandon scared everybody off with his beautiful sketch of traveling to Italy from
Trinidad and Tobago.
Trinidad. Yes, right. And I have to say, until this summer school, I couldn't have found Trinidad on a map. So, but I went and looked it up just because of you.
You're welcome.
Well, you know, yes, you can. I should always learn new things, and so, all right. So, joining us today, we have a couple of guests today. Subhamoy, whose name I'm sure I'm mispronouncing it because I just heard Lika pronounce it correctly, and is going to be giving us a talk on machine learning, and also I've been thinking about this introduction for a while. We're joined by various fields and areas have various people in them who oftentimes are just known by one name. So in music you have Madonna, in art you have Van Gogh, and in heliophysics we have Lika, who is the apparently walking around in the middle of in the middle of a nebulae, because as you bounce up and down, you're muted. So
I said it fits with Van Gogh.
Yes,
it's
right.
The
yes,
heart-shaped nebula, not by JWST. It's still Hubble.
And I see. Okay, yeah, you're the OG of space telescopes, as it were, right?
Right.
So, if you wanna, do you wanna introduce yourself, Lika, and say a couple of words?
I will, and you know, all the other things Nick say, don't worry. It's kind of continuous part of that music we were listening earlier. But the one thing where I feel guilty about and want to correct, I'm not a guest at this program. It is very unfortunate that this year I absolutely had not been able to participate. And this is the first time in whatever, 17 years or so. It's been very busy. I was supposed to give a talk, but I think you will hear from Subhamoy, that's how we pronounce his name,
Okay.
who is going to actually walk you through some AI ML, demonstrations, what we are doing with it. This is the tool of the future and present, I would say, for early career people. It's really important that you start learning it and adapting it. I'm a fixture in the field of heliophysics, much like the star field in the sky. They don't go anywhere, or if they do, very slowly. Welcome at the very last day, and sorry I couldn't participate more. Thank you, Nick.
Thank you, Lika. And so, I'll take on. Why don't I take on moderating duties this morning? Unless Mark or Christina really are anxious to moderate. Okay. So, Shubhamai, the way we've worked this is you just worry about your lecture. I will keep an eye on chat, and participants will, if they have questions, can either raise their hand or put the question in chat, and I will interrupt you at appropriate times if such questions come up. So, and we've got.
So, Nick, one more thing. I have a sharp cutoff at 7:45.
Okay.
Just wanted to let you know.
Okay, great. Thank you. All right. So, Shubhamai, if you want to share your screen, and you can get started.
Yeah. Do you see my screen fine?
Yes, it's great.
Yeah, so first of all, thanks to Lika and everyone for giving me the opportunity to present this. It's really a pleasure to be able to talk about the entire stretch of machine learning in the domain of heliophysics. So the plan of this talk is like this. I'll take you through some of the basic techniques or terminologies that are used in machine learning or AI in general, and then I'll show you what are the different areas. It may not be the most comprehensive list, but I will at least try to give you a brief overview of what are the different approaches that are being implemented from the machine learning side in the domain of heliophysics. And then depending on the time we are left with, I will take you through a Python notebook where we will show a machine learning experiment to classify solar images that we recently developed. Okay. So this is the title of my talk. Where does the artificial intelligence or machine learning stand in the domain of heliophysics? Now, before I go to the actual techniques, I wanted to show you what really we mean by saying AI or ML. So they are not the same. As you can see in this Venn diagram, the artificial intelligence is the superset, right? It combines all the techniques that enable the machines to behave like a human, right? To take decision like a human. Now, AI combines all the algorithmic approaches you are developing for your solar data analysis, also the ones which are not algorithmic, which are more general frameworks, and those are the machine learning approaches. So machine learning approaches are subset of artificial intelligence, and those are the approaches which don't need any explicit programming. You have a general framework and you have the data, and you train the model to learn an optimal set of parameters to really arrive at the desired outcome. So those are the machine learning models. And again, a subset of that is deep learning, which I'll come to explain you later. So I think you got some idea about how different these terminologies are. Now there are different approaches of machine learning, and broadly you can classify the machine learning approaches into unsupervised and supervised. So unsupervised means when you don't have So you are trying to do a set of tasks, but you don't have the supervision. That means you don't have the annotation. You have a large set amount of data with high dimensionality, and you want to discover different clusters or patterns in the data. So that is when we start using this unsupervised approaches, and these are two different variants of clustering approach. So clustering, so you can see in this diagram on the left that you have two axes. So these are called the features of the data, that encode the behavior of the data in different dimensions. And then what you do is you assign different centroids. Like you suppose you have this scatter plot and you want to divide this into 3 clusters. So you assign first different points in the feature space. So in this case we'll assign 3 points, and then you will try to evaluate the distance. So you can do Euclidean distances or statistical distances from the centroids to the data points, and you will cluster the data to the individual centroids depending on whether those data points are closer to cluster 1 or cluster 2 or cluster 3, right? So then you partition the data into 3 clusters, and you do it iteratively. By iterative manner, I mean that you evaluate the centroid again when you arrive at a cluster at the first step, and then you again assign those uh, 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 points again to the cluster centroid depending on their Euclidean distances, right? So when you converge, that is when you arrive at the clusters. And there are also hierarchical approaches such as DB-scan, which I will not explain at this point. And there are supervised learning approaches, and the support vector machines are very popular in the supervised domain. So supervised means, as you can see, that these data points already have colors. That means they have annotations before you are starting to train a model, right? So now you know that, okay, these are the points in the feature space that have annotations of, say, yes or no's or zero or one. So this is a binary classification, right? You have 2 types of annotation, 0 or 1. Now what you want to do by support vector machine is you want to evaluate a decision boundary, so which is this red line here, and this line is the separator between 2 classes, and the objective of this task is to arrive at the optimal decision boundary, which maximizes the distance from the neighboring points, which are the points which are touching this dashed lines, which are parallel to the decision boundary. So when you maximize that distance, that is when you arrive at the optimal uh, uh, decision boundary which separates these 2 classes. So in this case, as you understood, that there are annotations which are not there for the unsupervised case, and there are also approaches like decision trees. So decision trees are this a structure or branching which is encircled by this decision tree here. And so here you see different nodes, parents nodes and leaf nodes. So the parent nodes are different questions that you ask, right? You have the data, and you apply different thresholds to the data, and you arrive at this yes or no decisions based on the questions. So questions are the nodes here, and branchings are yes or no's. Then you arrive at another question, and then you go on till you reach the leaf nodes. So leaf nodes are the classifications, right? You have that is what you're optimizing this structure on. And you can also increase the depth depending on the requirement. So this is how you arrive at a decision tree, starting from your input and the annotated outputs or the targets. And you do it by asking different questions and then connecting them through yes or no's, right? So these arrows here through the decision tree shows how a particular inference is arrived at, right? Now you have, this is a single decision tree, and you can have a set of decision trees, right? You have a sample of data points, and you can take some random draws of the from the sample, and for each of those you can generate a decision tree like this. So instead of a single decision tree, you have an ensemble of decision trees. That is what you that is the basic concept behind this random forest, because you are randomly choosing the data as well as the feature set. So suppose you have 10 features, and for each of the decision tree you are dealing with 5 features randomly draw from those 10. And you can also change the feature selection criteria. You can change the probability distribution of the features based on the importance that you arrive at the first iteration, and you can do this iteration several times. So that is called iterative random forest. That is another variant of random forest. Then this neural networks feature, which we all are really excited about, and this is the basic this is the building block of a neural network. So what you have here is a set of inputs. So x1, x2, x3, this is the dimension of the feature vector. There are p features, and you have a target which is y. So in this case, y can be say either 0 or 1 if we are taking a binary classification approach. And so what neural network is doing is it is assigning different weights to combine the input features, and also there is a bias, right, which gets added to the weighted combination of uh, these features. And once you do that weighted combination along with the bias addition, you get z, and then you do a nonlinear transformation of z to arrive at the prediction, right? And then you have the target as 0 or 1, and you have the prediction as a continuous function which lies between 0 and 1, and you are trying to optimize the difference between the target and the predicted, and the difference is called loss function. And when you minimize that, you arrive at this set of weightages and the bias term, right? So if you can think of this now, so this is like a hyperplane, right? You have this linear combination of weights and a bias. So it is, if you put z equal to 0, so you get the equation of a hyperplane. So this is like a single layer neural network which is learning a decision boundary, like I have shown in the support vector machine case. But you can also learn nonlinear decision boundaries and any arbitrary shape you want. Suppose the data points in the feature space are quite clumsy, and you cannot draw a linear decision boundary to make an optimal classification between those. So that is when we come to this multi-layer neural network. So these are just layered arrangement of those units that I have shown. So this each node here again sees the weighted combination of input features, and then this bias is applied, and then output is propagated to next layer for each of the neurons in the input layer. And the layers that where this weighted combinations and non-linearities are applied are called hidden layers. And you do this, you traverse through the several layers and arrive at the outcomes. Right. And this optimization or finding this optimal weights happens through a back propagation algorithm, because this is a quite complex model. You can not just do the gradient descent optimization. So it happens layer wise, and it propagates through the entire neural network, and these weights get adjusted through iterations, and you apply at the optimal set of weights at the end. And now I have been talking about features a lot. Now let's see, when you have a data set which has several, say hundreds of features, right? So how do you visualize that in a more optimal way, such that the visualization preserves the clustering of the data in the higher dimensional space? So this diagram on the right is showing handwritten characters, and which are forming different clusters, right, in the feature space. And this feature space is here, it is 3-dimensional. I can take you to this page. It's quite fun. You can change your, so this is like, it's called MNIST data. So you have this images versus their annotated labels, which are the numbers 0 to 9 in this case. And you can see, so this is like, so this is like how different images of handwritten digits are forming different clusters, right? And you can apply different feature visualization or reduction techniques. So PCA is basically a feature reduction technique. So what you do is you have an input set of features and you arrive at a set of features from the input set which are linearly uncorrelated, right? And each of those features are linear combinations of the input features. And based on the variance of those arrived uncorrelated features, you reduce the features which don't really make any sense, right? And when you do that, you can say reduce a 100-dimensional feature set to a 3-dimensional feature set, right? Of course, you lose some information. It is not always optimal to reduce 100 dimensions to 3 dimensions, but at least you'll get some idea yeah, of how different clusters are forming. And there is also a technique called TSNE, which is called T-distributed stochastic neighbor embedding, where you preserve the distances that is there in the higher dimensional feature set in the lower dimension. So you are basically preserving the morphology, but and you are showing a trustworthy visualization in the lower dimensional feature space. So you can let it run for several iterations, this TSNE algorithm, and you can see that starting from initial arrangement of these clusters, how they are slowly forming more well-defined clusters with iterations, and you can see that all the ones are forming clusters, the sevens are going together, six are going together, and the value of this approach is that when you have this misclassification, right? Suppose you have a model, you want the model to classify an image into one of these digits, and if the image is not very well defined, it can uh, end up doing misclassification. So by looking at this feature set, you can understand where your misclassification is happening, because it is really difficult to put a decision boundary across that. So you can let it run for several iterations. You can see the iteration here is changing. You can play around with different hyperparameters here and see how after several thousands of iterations, you get more well-defined clusters of these 9 digits. So these are like 100 by 100 images. So you have like 10,000 features if you go by the individual pixels, and you are really by this approaches, you are seeing those 10,000 dimensional feature space into 3 dimensions. So that is the power of this approach. Okay, I will not spend more time here. So now coming to the deep learning part of it that I was showing in the first slide. So for the neural networks, you saw that you have images and you have a feature extraction step. So where you need some feature extractor, and that takes time, right? And you never know if you have enough set of features to arrive at the optimal outcome, right? So this is an example where given an image of a vehicle, the network classifies it into car or not a car. And there is a feature extractor that converts the images into set of features. Let's say now the number of wheels, the dimensions, etc. But when you are bringing the deep learning approach, you avoid this feature extraction step. So you give the image directly, and the model itself discovers the most important features from the image, right? So you don't need this feature extraction step. And then that happens by usage of convolution. And that is how we arrive at the convolutional neural networks. So to show you the motivation behind the convolution, so here is an image of a dog, which is 1,000 by 1,000 image. So you have like 10 power 6 pixels, and you have 1 million pixels at the input. So if you treat each pixel as a feature, so you have like 10 power 6 input features, and now you have a neural network which has 10 power 6 hidden units. So now if you connect each pixel to each of the hidden units, you have 10 power 12 parameters to learn, right? Which is huge and put serious computational burdens. So it turns out that the images you have this locally correlated structures, and you don't need to connect all the pixels to the each to the nodes of the hidden layers, right? You can do it by selective pixels. So that is done by convolution. So each neuron is connected to a set of pixels, and you slide it across the image, right? You multiply and add, and then do some nonlinear transformation. So you are doing parameter sharing, and also your field of view is limited. And by that, you are making use of the locally correlated structures in the image. And when you do this, cascade these several layers of convolution and nonlinearities, you end up extracting hierarchy of features. So you can see you are given the image of a cat or a dog, and you build a convolutional neural network to classify that appropriately, the image appropriately. So in the initial layers, you see that the model is learning more basic features like edges, curves, etc. And when you go deeper into the model, it learns more higher level features. So you are basically clubbing this lower level features to build these higher level features like nose, eyes, ears, etc. And then it clubs even further, and the final convolutional filters will learn the entire image, right? So that is how the hierarchy of feature learning takes place in the convolutional neural network. And the field of view also for each convolutional kernel increases as you go deeper, right? And now you got a brief idea about what all the approaches are quite popular in the domain of machine learning. And now let's see how those are being applied in the domain of heliophysics. So if you go to NASA ADS and you do abstract keyword search, and you give all these keywords like sun, heliophysics, space weather, so you can do all or and then and machine learning, and then you get this graph here, right? So you can see that there is an exponential growth. Although all the papers are not referred, but there is an exponential growth of machine learning application. And right here is the advent of STO, uh, which can be the driving factor of this exponential growth in machine learning, but that growth you don't see when you remove the machine learning keywords, right? So this kind of says that with the advent of new observatories or big data, right, with the STO, within the lifetime of STO, it will generate like tens of petabytes of data. So where machine learning is really inevitable. So to handle such data, learn patterns from this, you need some approach which is more generic in nature and which don't need explicit programming. So that is where machine learning is becoming really popular in. So let me show you what are these approaches that are being applied, what are the domains, subdomains within heliophysics where machine learning is being applied. We start from very simple things like data homogenization. So you have these observatories like SOHO and STO. You can use their overlap, temporal overlap, and train a model to convert SOHO images into STO images, right? And that stretches your baseline from one solar cycle to two solar cycles. And you can learn really important things by having a homogeneous data set instead of developing algorithms for this individual surveys. So like you can use a single algorithm for the entire homogenized survey. Then people are also using machine learning for solar cycle prediction. So you have they're using neural networks to do both temporal prediction and spatiotemporal prediction, which is shown here, the butterfly diagram, the sunspot butterfly diagram. So using the data encoded in this butterfly diagrams, they're trying to predict future butterfly patterns. Also, there is this solar feature segmentation here. You see this dark hair-like features, which are filaments. You have the ground truth masks, and you have the predictions. There are surrogate models. So there are different simulated simulations which take a set of say polarimetric parameters and convert that into model atmosphere, and you can really make it faster by replacing the simulation model with a machine learning model. You can do inverse problems as well. And then there is this space weather forecasting applications where machine learning is becoming really popular, because again you are utilizing the big data. So now to give you a bit more idea about the data homogenization, as I was talking about, you have the solar cycle, and within the solar cycle you have the advent of different observatories, and they have different temporal overlaps. You can really utilize those overlaps to build a homogeneous survey across this entire time span. So this is a particular work by Andres, so where he is using the temporal overlap between SDO and GONG and SDO and MDI to get a homogeneous survey of magnetograms. You can see that the input in the SDO, the MDI data. So they do this transformation patchwise. They break this entire solar disk into smaller patches. They do alignment of that with the target SDO patches, and then they build a neural network, convolutional neural network architecture that transforms this low resolution MDI patches to high resolution SDO patches, right? And when you train this model with different augmentations across a long duration, you end up getting this ML predicted outcomes here. So you can see the features that were hardly understandable in the lower resolution are now being more well clustered here. But there are problems, right? This is a very ill-posed problem. So you have a single pixel and you are blowing it up into 4 pixels. So it can happen that you don't have the information, but where from you are bringing the information, right? So that is where the context information is important. Maybe in the higher scale or the surroundings of a pixel is important to really understand the smaller scale informations, right? Maybe that information is there, and that is how these models are understanding how a coarser pixel is corresponding to finer pixels. But again, I said it is ill-posed because there are several combinations of this 4 pixel that can correspond to a lower resolution pixel, right? A 4 pixel, because in HMI has like four times better plate scale as compared to MDI. But that is constrained by the context information. That is what this deep learning models are making use of. And as I said, there is this loss function that you are minimizing to arrive at outcomes. And this loss function you can define in different ways. Here they are using different metrics which are trying to constrain the outcome by different physical expectations. So that is how the loss function is important, and you can generate the custom loss functions, which are really important to make your results physically consistent instead of going blindly with the available loss functions. And there are also approaches of these image transformations which are really being popular nowadays. So you have these near side observations in magnetograms, but you don't have the far side magnetograms. And it is really good to have the far side information for having a snapshot of the entire sphere of the sun, right, instead of a single side. So you can see the simultaneous evolution instead of waiting for the sun to rotate into the near side view. So these authors, what they have done is they have used the temporal overlap of SDO, AIA, and the stereo data, right? So, and they have done a mapping between so here you have the input as STOAE and the target as the STO HMI. So you have also the 304 data from the stereo, right? But you don't have the magnetograms from the stereo. So if you train a model to convert 304 to HMI, you can convert the stereo data into magnetograms. And stereo has different vantage points. You can get the far side view of the magnetic field. So that is what they have done, and they have applied a technique called CGANs. So CGANs are conditional generative adversarial networks which use of this generator and discriminator approach. So there is this adversarial learning going on. So the generators are generating this magnetograms given this 304 angstrom images. So generators' objective is to generate fakes which are as good as possible or as close as possible to the real ones. So with the training, the generators become as good as possible in generating fakes, and the discriminators become as good as possible in distinguishing fakes from the real ones, right? So there is this adversarial learning going on to arrive at this outcomes. But there are problems in these approaches, and there is a lot more detail how you can really improve these approaches. And here in these authors, what they find is this approach is efficient in finding these polarities in the larger scales, but in the smaller scale, these are really inefficient, right? So that is where the application of machine learning is really, you really need to think whether your data that you're putting as in input is really able to capture all the information that you want to see in the output, whether a single channel is good enough or you need multiple channels. Right. And there is also solar cycle predictions applying this feed forward neural networks and also recurrent neural networks which make use of the causality in the data. So you are not only feeding the data forward through the neural network, you also allow looping. So you take different time steps, and each time step you take the outcome and feed that into the neural network which is capturing the next time step, and that is how you go ahead with time series forecasting. And then we have solar image classification or segmentation. So you have this set of image patches. Each of these patch represents a feature. So the one which is showing this bright flare ribbons, there is this prominent structures. Then there are sunspots, and if you can build a single model which single machine learning model which can classify this into one of the 5 classes that I was talking, filament or flare or prominence or white sun or sunspot, right? One of these classes that becomes a multi-class image classifier given a solar image. So you see in the bar charts what are the probabilities that are generated by the neural network for different classes. So given this flare image, it says that it is more probable that this image corresponds to a flare ribbon, and the next high probabilities for sunspots because of there are some dark features here. For like that, you can try to understand the decisions made by your neural networks. Also, there are the segmentation tasks. So instead of classifying the entire image, you are classifying single pixels in the image. So that is how you are generating binary masks which are of the same size as the input image through again a convolutional neural network. There are inverse problems, right? So there are simulations which take Stokes parameter and convert that into model atmosphere, right? So you can replace that model by this encoder decoder architecture here. So you are encoding the relevant information from the Stokes parameter in progression, and then in the decoder part you are decoding and bringing that to the model atmosphere parameters, and that you adjust this parameter weights through optimization, right? So you can generate physical parameters like your temperature, the velocity, the magnetic field as a function of this optical depths. So why these inverse problems or surrogate models are really desirable? Because they're really fast, right? These machine learning models, the training phase take a lot of time, but the inference is really quick. So that is how it is important that you try replacing these models with this machine learning models to have fast inference. And lastly, there are space weather forecasting applications, but here you need to really be cautious, because your predictions may go wrong and it can really affect our communication satellites, or it can pose really good big radiation hazards. And if you want to avoid those, if you want to avoid the false predictions, you need to really look at different metrics, right? So just the accuracy is not good enough. You need to see how good the model is performing for both positives and negatives. So there are these false positive rates. So where you are saying that how many predictions are negative predictions are wrongly predicted as positive in your set of outcomes, right? It's a false positive rate. There are also probabilistic metrics like Bayer score. So you have the targets as yes or no's, and you are, instead of predicting yes or no's, you are predicting probability. So for a user, it is really important to understand the probability of an event happening instead of a deterministic outcome, which is just yes or no. But the neural networks are not really good in producing proper calibrated probabilities. Of course, with a nonlinearity, you are producing some number between 0 and 1, but that doesn't mean they're real probabilities. So you can calibrate those neural network outcome and post-process those to predict true probabilities, which are more close to the real event frequencies, right? So that is the reliability. So when your probability is reflecting the occurrence of positive events, that is when you can say that your probability is the real probability. So you can take the neural network outcome, you can generate different calibrators, and you can transform those neural network outcomes into true probabilities. This is a snapshot from our very recent work. Of ACP forecasting, where you are training a classifier, and then you are taking the classifier outcome and calibrating it to represent the probability of event occurrence, right? We have these flares as the reference times. We have different in situ and remote sensing inputs. Remote sensing such as magnetograms, in situ such as interplanetary magnetic field measurements, and you want to forecast what is the probability of occurrence of solar energetic particle at L1 point within 6 hours from the flare onset, right? So that is the where the probability comes into the picture. And now the last part of my talk is okay, you understood that the neural networks are really the deep learning models are really versatile and they can do different tasks, but how trustworthy are these outcomes, right? So here is the motivation for you. So you have, say, an image classifier which was trained to see two different faces, and it was trained to predict the probability of um, uh, of, of of a face representing an image of certain so the x-axis are the two possible classes shown in the training phase, right? And then in the test phase, if you show one of those two faces, it will the network will be really efficient in predicting the probability of that face being there present in the image. But if you show an unknown face, that is where you expect that the network will be really neutral, and it will say, okay, the probability is 0.5 for both the classes, because it corresponds to neither of those. But in real, what happens is these networks will have really biased outcome, and they will be really off from the reality. So instead of a single model, if you can ask the same question to a set of models, that is where you start getting some value of having uncertainty instead of a point estimate, right? So when you show a face which was well represented in the training set, the ensemble members will converge, right? They will have decisions close to each other. But if you show the unknown face, they'll really diverge and say show different outcomes. And based on their agreements or disagreements, you can make your outcomes actionable, right? So that actionability is important, and that is where instead of a single model, the benefit of having a model ensemble becomes really apparent. So this is a recent work by us where we are doing classification of videos, and instead of training a single model, we are training a set of models, and these are identifying if an emergence event is happening within a video. So you can see that having an ensemble of models, you can really understand the uncertainties. You can see in the unstable inference region in the true positives, if you did not have an ensemble, you could get an extreme outcome which is really off from the reality, but having the ensemble, it really drives the median to above the threshold. So, and also apart from this uncertainty, if you can understand the interpretation of the models, what is it that the model is really looking at to arrive at a prediction, right? So you will see that when you apply more complex models, your depending on your application, the prediction accuracy will improve, but also the model will become less explainable, or the interpretability will reduce with the complexity, right? So the x-axis is increasing explainability, and y-axis the prediction accuracy. So higher the accuracy, smaller is the explainability, right? So there are different approaches to really understand if what these black box models are really learning. So I am showing one of these approaches, which is called the saliency map. So this frame represents the onset of an emergence event, right? And okay, the model predicts this as yes. Okay, so in the video there is occurrence of emergence, but we want to know where in the frame the model is really looking at to say that it is an image, whether it is giving the right answers for the right reasons. So the saliency map changes the inputs and predicts the class probabilities. And when you change that, you find the importance of different pixels in driving the outcome. So the brighter pixels are more important than the darker pixels. Small change in the brighter ones will cause a large change here event probability in the outcome. So you can see that the bipolar emergence here is co-aligned with the brighter pixels in the saliency map. So now you really know that your model is looking at the regions which it should to arrive at the prediction that it is an emergence. So also you can repurpose the model. This is a model which was trained to do only classification to say whether emergence happens or not. Then you repurpose the model to say where in the video the emergence happens. So you can see this blue to orange transition. Say right. So if you look at the color map, you can see when at this stage only 2 models were saying that it is an emergence. But when it comes to this territory, all the 10 models say it is an emergence. So by this ensemble approach, you can also repurpose your model to do a higher level task than it was originally trained for without explicit retraining of the model. So when you are able to do this repurposing, it also increases the transparency of the model, right? So you can say that, okay, the model is really understanding the dynamics in the video to say that it is an emergence event. So to summarize, so as you could see, we are entering the petabyte regime in the heliophysics, and machine learning is really becoming inevitable in that we have SDO, we have decreased. So we are going to have a really huge data in multiple modalities. You can think of magnetograms, multi-wavelength data. So it is really important that you make use of the available machine learning techniques, and you could see that machine learning can also significantly improve the observational baselines by doing this homogenization of multiple surveys. You can, but you need to really be careful when you are applying this machine learning approaches. You should not only focus in producing good looking data, but that should also make sense, that should be physically consistent. So you can do this by uncertainty estimation, trying to convert these black box models into interpretable models, so that you really know how the machinery is working and what parameters it is actually learning, whether it is giving right answers for the right reasons. So with that, I will end my talk, and I think, do we have a little time to take you through this notebook that we have
To
prepared?
do something fun, yeah.
Okay. Okay, so I will just put the
And in the meantime, so that was a wonderful whirlwind tour of machine learning and heliophysics. I'm
thank you.
sure people have questions, so put questions in chat. And
Okay, so I put the link of the Google Colab notebook in the chat. So I will, please take a look at it, and you can run at your leisure. Yes. Oh, okay. Is any of you? I'm sorry.
Yeah, I was just wondering if any of the students are
Okay.
using
Okay, I'm sorry.
any unsupervised or supervised or any type of statistical modeling, graphical neural networks.
Okay. So I'll briefly take you through this, but at your leisure, please feel free to take a look at it. And if you have problems or questions, you can come back and ask me. I can try to fix those. Okay, I think I'm not sharing my screen. Do you see my screen?
we do now, yes.
Okay, so this is the Colab notebook that I was talking about, where we tried to do multi-class solar image classification, and this will take you through the flow of this approach. So we start with importing necessary packages, download the dataset, then convert the data to make it suitable for training a deep learning model to classify those solar images into different target features. And then you can evaluate the model, do the feature analysis, and then there is this fun part, which is the interpretability. You can try to understand what the model is really learning from the data, and we are using saliency map there. So I'll show you a few steps how we do it. So you start by importing the packages. We are using TensorFlow here, which is the machine learning, I mean, especially deep learning neural networks and deep learning framework in Python, and Keras is a layer on top, which makes it more user friendly. And there are other basic packages such as NumPy, Matplotlib, etc. So after this cell is done, you go to the downloading the images from the Dropbox location that we have stored these images in.
Subhamoy, can I interrupt with a quick question?
Yeah, sure.
So what packages? Having never used Colab, so I'm not sure quite how that works. But what packages do you have to install locally?
You don't have to. So Colab you are using, yeah, it is just cloud-based, and if all these packages are pre-installed in Colab. You can use the free Colab, or I have a Colab Pro, which is a paid version. And if you upgrade to Pro, you can have more uninterrupted access to GPUs, more RAM, etc. So you will have faster runs. Other than that, normally you don't need to install anything in specific. So this is the import of packages, and then you have downloaded the data, and then you start visualizing. You can also run this different shell script in Colab with this exclamatory symbol. you load the training and test data. So this, let us see what this means. So we have these images which are vectorized, and we have the corresponding image levels, which can be uh, uh, different types of solar features. So we have this, these are the target levels, which are called also ground truth levels, which are from 0 to 4. So 0, 1, 2, 3, 4, you have 5 levels, and you can see how balanced is the data by seeing the histogram of those levels. Right. So I will urge you to take a look at this notebook, and feel free to edit this, but please copy that to some other location. Otherwise, all the changes here will be overwritten, right? So you can just copy, download it, and again upload it to Google Drive and open Colab and run it from that other location where you have stored it. So you have, like I said, there are 5 classes. So 5 classes are these: filaments, flares, prominences, quiets, and sunspots. So you can just take the arrays, reshape into 256 by 256 images, and these are the different images of sunspots. You have group of sunspots, or you have single sunspots. You have other features which look like this. You have the filaments, which is this dark elongated features. You have these flares, which are bright regions. You have prominences. You have quiet sun, which is the background, and you have the sunspots. You have 5. So you have images as input to a model which correspond to one of these 5 classes, and your model should correctly predict the type of the image you are feeding it with. So for that, you build a deep neural network. So this is a network architecture it takes. So it is the input which has a particular shape. So I just resized this image into 64 by 64 to make the process faster. You can try 256, right, by changing this is set equal to 256. So you have this 2D convolutions happening. So this 3 by 3 is the convolution kernel, and 64 here is the number of layers that you want to transform that the input images into. Then you do some normalizations, so to standardize the feature layers, to bring the mean and standard deviation into some known values, and those are the trainable ones. And then you apply some nonlinearity here. There is one nonlinearity which is very popularly used in deep learning called ReLU, which is max of 0 or x. So if it is less than 0, your input, then it becomes a y equal to 0 line. Otherwise, it becomes y equal to x. You have max pooling, right? That is just shrinking the image and making the field of view of each subsequent convolution pixel higher, right? That's how you are learning the hierarchy of features, right? So you have this set of operations, and there are cascades of these operations. So with when you go deeper into the model, you see the number of feature layers are becoming bigger and bigger, and you are getting smaller and smaller feature slices, feature layers, because you are pulling it, right, to shrinking the size. So that's how you are learning the hierarchy of features. And at the end, it becomes the images become a vector. And when it becomes a vector, then you apply the fully connected neural networks. You have some regularization by dropouts, then activation, and at the end, you use this dense layer, so which has the size of 5, because we have 5 targets. So the model should predict that this image corresponds to one of these 5 classes. So the outcome should look like 0, 1, 0, 0, 0, right? So if it is the second image type that the image corresponds to, second feature type that image corresponds to. So you have a dense, and you have an activation which is called softmax, so which you take the outcome of the neurons and you normalize it so that your sum of outcomes are 1, and you take the max of that, right, by taking exponentials, and the max gives the image, the feature that the image corresponds to. I'm sorry. And then you define the loss function and the optimizer. So your loss function here is the categorical cross entropy, because you have 5 different categories to classify the image into. Otherwise, you can use binary cross entropy. and you define the optimizer. Here it is stochastic gradient descent, and you have hyperparameters like learning rate, momentum, etc. You can also see how the model architecture looks like. You can see how many parameters are trainable within the model, how many are non-trainable, right? And then you have this encoding. So before you start training the model, you need to encode the targets or the ground truths into one hot encoding. So if you say target is 4, you change it to 00010. If it is 5, it is 00001, like that. So it's 1 to 5, you are encoding into the zeros and ones, which is called one hot encoding. And those are the targets for those 5 output nodes that I was showing. You can also apply augmentation to improve the diversity in the data set. And then you can start training the model, and you'll see different iterations here. So these iterations are called epochs. So each epoch will have a number of steps again, and each step is seeing a chunk of the data, which is called batch. And after the model sees the chunk of the data, the model parameters get updated. And after you complete seeing the entire data, it becomes an epoch. And you go through several such epochs or iterations, and you stop. So you have a training set and you have a validation set. So training set says how good your model is fitting the target, right? And the validation set is how good it is able to generalize on unseen data. So you have a good balance of the memorization and generalization. So validation set is giving you the idea of how good the model is in generalizing on unseen data. So you will stop training the model when your validation stops improving. So you can see the statements right here, validation did not improve. So this model did not get saved. It gets saved only when the validation accuracy improves. You can see here with the number of iteration, how the accuracy is improved, how the loss function gets minimized. And then once you're done training the model, you evaluate the model on the test set and see how good it was statistically on all the unseen data. So you have this metric called confusion metrics. So all the diagonal elements are true predictions, and all the off diagonal ones are the false predictions. And you can see that there is a significant crosstalk between the filaments and the quiet sun. I'll come to it later when you look at the feature visualization. So you define another model which is called model TSNE, which just trims the model to take a feature embedding. So as I was showing, like you can make feature reduction and see that in a 3-dimensional space, right? So instead of having 3 dimensions, you have like 256 dimensions as the outcome of this model TSNE. Sorry. And then you can do a reduction to a 3-dimensional space and visualize it. So you have a feature vector in this one of this which look like this. It's like some positive and negative numbers, and then you visualize those into 2 dimensions and color them according to the classes, right? So what you can see is these blue ones which are filaments and the purple ones which are quiet, and there is a margin right here, right? So it is very difficult to draw a decision boundary, and that is why the model is making mistakes in classifying filaments or quiet sun. Is misclassifying some of the filaments into quiet sun because your decision boundaries cannot be appropriately placed given the complexity of the model. You can also see this in 3 dimensions. So you can, when you hover around through these points, you can see their corresponding classes. So this is like it shows classes quiet, and it shows 3 components. And you can see right here there is merging of blue and purple, right? So there is quiet and there is filament, and that is how it becomes difficult. And you can also do the principal component analysis where you see more merging, right? And this is not really the representative of the higher dimensional feature space, because these are linear feature reduction, whereas TSN is non-linear. Now there is another fun experiment. What if you did not have a deep learning model? If you treated the input image itself as a set of features, and then you just reduce the dimensions into 3. So you can really see that this with the absence of deep learning, it becomes really hard to separate the features or draw a decision boundary. And the last part of this is the saliency map, right? So you install the package which is not pre-installed in um, Google Colab, so by this simple command, and then you need to change a code slightly. So you first copy the code, remove the existing code, and then make the changes on the copied code, and then write it to this location, and then you import this package. So it's called Keras visualization, and then you run the saliency map. So this is the original image of a flare, which is the bright regions in the image, and you can see the model correctly predicts this as flare. And now you want to see what are the key regions in the image that are driving the prediction. So that is the saliency map. So you see the bright pixels, right? So which is co-aligned with the flares. So bright pixels are the one which have the efficiency to drive the prediction. So they're co-aligned, and you can now say that, okay, this prediction is really fine because the model is looking at the flare regions. It is not looking at the background and saying it is a flare. But you can find examples of those false classifications that I was showing, where there are filaments but the model misclassifies as quiet sun. And you can see when you run this code, you will see that the model looks at the background, not on the filament regions, and that is how it ends up predicting quiet as the dominant probability for that particular image. Okay, I think that's all I wanted to say. And when you run through this, if you get any problem, you can contact me. Yeah, this is my email address. Yeah, that's it. That's all I wanted to say today.
That was great, Subhamoy. Thank you so much for ending our the content. And so we'll take any questions for Subhamoy on this. And while people are either thinking about questions or raising some in the chat, maybe Mark or Christina have some questions. Or not? Oh.
Yep. No. It's amazing how quickly machine learning tools are now really taking off. The first time I saw a neural net was as a postdoc in the early 90s. And so it's been 30 years, but just seeing the exponential growth, and part of it is you know, the web optimization community, but also the access to big computers and big data. So great. And I urge all the students, even if your work is not directly related to classification or identification, to dive into the literature, because you never know what tools can be useful for you. I have a new PhD student who's using research from the acoustics community, noise cancellation, to do noise cancellation for magnetometer instrumentation. So learn from what's going on.
Right.
Oh, so Lydia's got a question in chat. Oh, yep.
I don't have at this moment, but I can. There are Bayesian approaches that we are planning to apply for some of our problems. I can point you to the resources for that, but I don't have a notebook ready to do that exercise at this moment.
Great, thank you. What is do you have a favorite application, or the gold standard of a success story for machine learning?
Sorry, can you say it again? I was distracted.
What's your like gold standard, the thing you point to and say, here, machine learning has like changed this, our understanding of this thing, and that's.
I think it's difficult for me to point to a particular example, but I think in general, when you make these models interpretable, that's when you understand the magic, or what people call this as magic. It is not a magic, and it make it more understandable, and you really look through the model and you look through the machinery of it. So that is what is really exciting for me, like to get to take the model and totally decrypt it and see what it is learning, how the information flow is happening from the beginning to the end. And that's what the interpretability side of machine learning is really, and it will be really exciting. So suppose we have a set of inputs from our physical understanding, and we have a target, but we don't know the mapping because we don't have a physical model. But we know that there exists a mapping, but we don't know what the mapping is. So if your machine learning is helping to find a mapping, and if you understand how it is doing the mapping, maybe you will be able to find some new physics from it. So that's when that's where I think this approaches are really exciting. So to really try and understand what it is looking at, and how the information flow is happening.
Okay, great. Again, thank you so much for a great talk. That was a whirlwind tour and a lot of interesting applications, particularly on the solar side. I'm sure there's other applications on other areas as well that could be, as Mark says, magnetometer data is data, and it doesn't matter. Nobody cares where the machines don't care where it comes from. They just will do their thing. So
Right.
right. All right. I think at this point in time, why don't we take a 5-minute break? And when we come back, Mark is going to give us a retrospective of the work of Eugene Parker and George Siscoe as our final lecture of the summer school. So great. So we'll be back by 20 after, and I don't know what the. Be back in 5 minutes. Okay, great. Looks like we've got a quorum, Mark.
Okay, so let me share my screen. Awesome. So just going to briefly touch on a couple of very influential heliophysicists that have connection to the heliosphere and space weather. Eugene Parker and George Siscoe, both of them passed away this year. You can solar and space physics is a very interesting field that, in one sense, we're very new, essentially the space age, and we're not uniform at all because we really grew out of a lot of different disciplines. Of course, astrophysics, studying the sun as a star, has been around, and we've talked about Young and Hale and Babcock, and using the Zeeman effect early on in the last century to understand the role of the magnetic fields and the sun. But it really took the advent of space-based telescopes and coronagraphs before heliophysics really took off. Sort of the discovery of the active sun was waited till the 70s and actually early 80s before things were going on and understood. My first JGR paper was in 1987, where we ran a hydrodynamic code of essentially shock waves coming out of the sun, and using a very early heliophysics system observatory back in the 80s, when we had Voyagers and such that were running out, and trying to figure out what was the longitudinal size of some of these structures. But those are all associated to flares because coronal mass ejections weren't really part of the literature yet. But many of the folks that really made the name for heliophysics in the late 50s, early 60s were still active, and in one sense kind of depressing. They were essentially my age when I started in the field, and now 30 plus years later, they're retiring and in some cases passing away. So just wanted to spend a few moments to introduce you to Eugene Parker and George Siscoe if you haven't had a chance to meet them. So we've seen Parker's name quite a bit, sort of one of the giants of our understanding of the heliosphere, and really his paper in the 1950s essentially led to this concept of the solar wind and magnetized solar wind. And for a native Michigander as myself, he was born and did his undergraduate here in Michigan at Michigan State University. But he went off to Caltech, do his PhD, and ended up as a professor at University of Chicago, where he spent his entire career being able to work with a lot of astrophysicists to understand the sun as a star in that context. And we briefly mentioned the heliosphere in sort of an astrophysical context. And so part of the thing that makes Parker's seminal paper so important is it's not only important for understanding our sun and our heliosphere, it really gave rise to this sort of comparative stellar heliospheres. And so now as we are able to take images and a variety of wavelengths of other star systems, and knowing that many of them have solar systems or exoplanets, these types of astrosphere images where we can see the star and it's moving through its interstellar medium, setting up these bow waves or shock waves, these little bubbles or cavities. And so Joe Giacalone was talking about potential, what does our heliosphere look like? And the croissant model of Marav Ofer, you can sort of see a little croissant here, but you could also see more of a spherical object here and more of a comet tail one here. So depending on the relative motion of the star through its interstellar medium, and as Marav is trying to point out the role of the interplanetary magnetic field and its connection with the interstellar magnetic field as it goes around with the galactic magnetic field can have big impacts. So a lot of the astrophysical research looking at the local environments around some of these habitable star systems, we're just essentially using what we know about the heliosphere to understand those domains. So this is a little video that NASA put together, and I'm just going to show it to give you a sense of how NASA has tipped its hat to Eugene Parker. And let me know if you can hear it.
We cannot.
You can or cannot?
Cannot.
Okay, so I guess when we start, we have, okay. Well, I'll just leave this as a link. When you start the Zoom, you need to, let me see, I need to be able to click here, share sound. So let's see if that works. Okay, let's see if this works. And if you can yell, Nick, if you can hear it.
Yes.
Well, the sun is the primary puzzle in the universe because it's the one star we can observe in detail. And stars are complicated things. You can't imagine all the strange things that have been discovered in the sun. Let's see, the silver surface of this gets to what did I hear, 2,500? That's incandescent, isn't it?
It is my great honor, a few days before your 90th birthday, Gene, to announce that we're renaming the Solar Probe Plus spacecraft to be known from now on as the Parker Solar Probe. Congratulations.
I was very moved by the fact that that spacecraft is going off into the night sky and he'll never come back. When you have a space mission into an unknown place, you find remarkable things that you did not anticipate.
Okay, so just some highlights. I mentioned in the chat the other day that I had thought that Parker's contributions to our understanding of our sun and the heliosphere were so important. He was considered for the Nobel Prize, but didn't win it. But when you think about what he did in the 1950s, and Joe said that when he feels like he's doing a lot of cool work, he just goes back to look at Parker's papers in the 50s, and essentially he defined a lot of fields. His paper on the interplanetary gas and magnetic fields essentially was the one that outlined the solar wind and the interplanetary magnetic field, and even earlier, he started thinking about stellar magnetic fields, and so developed a hydrodynamic MHD model of dynamos. Essentially, he won every major science prize and medal that the world offers astronomers and space physicists, including the National Medal of Science, which is given by the President of the US. And then ones that carry a lot of money, the Kyoto Prize, I think like $1 million or something like that. But what's pretty interesting about Parker is that he was a single author of almost all of his papers, and he had all of his students pretty much. There are a few Jacobi and Parker papers and others, but usually he had his students publish their papers independently as well. So the other giant associated with the Heliophysics Summer School was George Siscoe, who also passed away earlier this year. George was a mentor of mine. We overlapped at a couple of places. He was a longtime professor at UCLA, where I spent part of my career. And then he moved to BU after late in his career. And that's my PhD alma mater, so connected with him. And his wife, Nancy Crooker, who was also a leader in heliophysics. But another sort of early pioneer in heliophysics, Bent Sonerup from Dartmouth, wrote a retrospective of his own career. And in that paper, he talked about George Siscoe as his teacher and mentor and intellectual leader. But he finished it as a gentle soul. And George Siscoe was definitely a gentleman and a scholar. And this picture is of him after he retired from space physics. He and Nancy moved to Maine, and he opened up a bookstore called the Old Professor's Bookshop. So he loved books and rare books. So what are you going to do for your next encore after you finish your career? So what was really interesting about George was his depth. He essentially wrote the seminal paper and then many of the follow-up papers with his students and postdocs, but also the breadth. He tackled all of heliophysics. And it's one of the lessons that I learned early on in my career is that people are going to find something to complain about you. And one of the things that you might have your career characterized as either too narrow or too broad. And so what I learned was you should do what you want because people are going to find something to complain about. So if you really are interested in a topic, become the world's expert in it, and that will carry you a long way. Or if you're interested in a lot of different things, go ahead and do it. Blaze your own trail. But the interesting thing as a student and an early career scientist at meetings and conferences and workshops where George participated in, he was also often the intellectual glue. There's a lot of different arguments on which model is best or which conceptual model or whatever. And he would always try to bring the community together with sort of conjectures. So he would try to, if somebody was introducing a new model and people were tearing it apart, he would try to summarize that model with a conjecture. If this model is right, then I conject that this should happen. So essentially a good physicist, what should we look for in observations or data to either prove or disprove or to support or not support? So that I think is part of his contributions. But we're recognizing him today, not only because he started the Heliophysics Summer School with Carl Schreiber back 16 years ago or so, but he also was the one who coined the term heliophysics. And he also was one of the leaders behind the entire discipline of space weather. So a lot of the work that he had done in setting up the NSF GEM community back in the mid to late 80s gave rise to thinking about the societal and technological impacts of solar and space physics as its own independent research area. And so space weather today essentially owes its birth to George Siscoe. So everything that we were talking about in the summer school, this connection between the sun and coronal mass ejections and the solar wind and interplanetary magnetic field with the geomagnetic field and the energy dumping into the ionosphere and thermosphere through the aurora. And these new types of observations that were developed because we needed to know the drivers of the system. And so the SOHOs and the SDOs and the ACEs and the WINDs and the DISCOVERs giving way to the entire heliophysics system observatory is essentially George thinking about this connection. So Lou Lanzarotti, another giant in the field, has developed a schematic showing all of these technological connections that I'm sure all of you have seen before. But when you think about space weather, think about Siscoe as well. So I'm just going to stop there and wanted to know if anybody has any questions. What I have found interesting in my career is I love the human aspect of the field. When you think about, I showed that picture early on of the Solvoy conference that had Einstein in it, and next to him was Marie Curie. But recognizing at the time, scientists attended meetings, but if you were going to go to the US, you were on a boat, right? There was no airplanes. And so it would take weeks. So you would essentially spend the summer in the US, and then you would take a train to Chicago to visit some folks at the University of Chicago, or go to Yerkes Observatory, or take the train all the way to California, to Sacramento Peak or wherever. But those were, 6-month journeys. And so you were exchanging letters with these people instead of emails. And so everything was a lot slower, obviously, but was still based on people and interactions. And so even though we're a much faster paced interactions, you should look at everybody's name. And hopefully in your breakout rooms, you got an ability to look at somebody's face, because this is going to be your cohort that you'll be working with and collaborating with and writing papers or developing new Jupyter notebooks to do machine learning or whatnot. But any questions on some of that history of heliophysics or space weather or Eugene Parker or George Siscoe?
We'll make sure to have the screenshot of all of us on the on archives, so that 20 years, 30 years from now, when we've got 5 Nobel Prizes in the group, we can and chairs of the decadal surveys and
Yep.
and fellows of the AGU here, we can point to all of you and say, look, here you were.
Yeah, Christina Cohen was is the past president of the AGU's Space Physics and Astronomy section, and Nancy Crooker was as well. And so when she was elected fellow of AGU, she always thought that was such a sexist thing. Why are you a fellow? And so she actually dressed up in a tuxedo for her fellow. So that's the type of people or person that Nancy was. Yeah, one of the advantages of the field as well is we're relatively small. Depending on how you want to include it, probably 6,000 to 8,000 people globally doing solar and space physics. So we're about the same size as the American Astronomical Society, which is the international group of astronomers, but focused in North America. So one of the nice things is you get to know each other, and so figure out these networks.
I just went running off to get one of my prized possessions. I don't know if anybody can see that. It's a little. You might have to like focus on me for a minute. But I went up to Belfast last summer, and so had an opportunity to stop in to the bookstore and have dinner with George and Nancy. And this was one of my acquisitions at the old professor's bookshop. So he had an absolutely eclectic and stunning collection of across all of Aristotle's categories of knowledge. So he had a stunning collection of books that covered the whole thing.
Yeah, my oldest sister is an archivist, art historian, rare book person, and so she, as a gift, bought me a intro astronomy textbook from the 1830s, right? And so you think 1830s, you know, not only was it before Hubble, so everything was one galaxy, it was before J.J. Thomson, so we didn't even know there were subatomic parts. It was before Maxwell. And so what was astronomy like? And so that was fun. And then I realized you can spend a lot of money if you want to get into rare books. So I've been collecting rare books, but on the space age rare books. So original Alphane books or Fred Hoyle books and stuff like that. And what's funny is that a lot of the books I buy, the person who owned it, I knew, you know, like Charlie Kennel or whatever, must have sold his collection to somebody, but it's new enough that everybody who would have bought a Akasofu book on the substorm is somebody in the field. But cool.
Okay, great.
So it's all yours.
Sure. So so we've got a little bit of a choice. I would like we have a wrap up session, which will be after our meal break. That is going to follow this. So our choice is to have a usual. The choice is to have a usual half-hour meal break, and then come back. And the wrap up session is going to be no more than an hour. I think the three of us have a few words to say, but also we'd like to get a little bit of feedback from you, in particular about the structure of the school going forward. We have an idea, and as participants in the school this year, I thought you might have some feedback on how that might work. So the choice is, so you get the choice, here, I'm going to do this way. We'll vote by stamps, right? So this will be I'm going to add a new one. So, 45, so 30-minute break. Or 45-minute break. And so 30-minute break, we get it done, we come back, we talk for no more than an hour, and then we're done. Or a 45-minute break where you have a little bit of extra time, we come back at half past the hour. Okay.
Looks like people want to get on with their day or go to bed.
So last chance to vote. Going once, going twice. Okay, so based on the votes, we'll do a 30-minute break, and then come back, and we have a little bit of a wrap-up session. While you're on break, you should have received a message from SurveyMonkey to complete a survey. I'd like you to complete that in the next week, but you may want to take a quick view of that, just a scan through and see what kinds of questions we're asking about. So it's a fairly detailed survey on what we've done over the last couple of weeks, and so there's some detail and interest, but certainly this will give you an idea of the sorts of feedback that we're looking for, and you can also speak to that during our wrap-up session. So we'll see you in 30 minutes, so quarter after or so, maybe 20 after the hour, or 10 of the hour if you are in the half hour thing, I think. So 30 minutes full. All right, we'll see you then.